Hi, we're up a creek and we're going to give you a more technical overview of our senior project.
As discussed in our intro video, Up a Creek collaborated with the propulsion team, Without a Paddle, to create a 14-foot solar-powered catamaran to compete in the 9th annual California Solar Regatta boat race, hosted by the Sacramento Municipal Utility District. Up a Creek was responsible for designing the sub-assemblies of the hull of the catamaran, specifically the pontoons, the bridge, which supports the pilot, the middle bracket, which interfaces the pontoons and the bridge, and the mounts for the solar panels. The final design for the hull came out to be roughly 14 feet long, 2.2 feet tall, and about 8 feet wide.
The final design for our pontoons utilized two airfoil shapes and was a loft between them. It was 10 inches deep, 14 feet long, and 15 inches at maximum width. To analyze the pontoons, we used two well-known boating parameters, the length to beam ratio and the prismatic coefficient. We also analyzed the amount of water the hull would displace to know what amount of weight it could hold at our desired waterline. And finally, we analyzed the drag on the hull using a tool developed by MIT called X-Foil.
For the pontoons, we decided to use XPS foam for the core and cover it with 6-ounce e-glass laminated with West System epoxy resin.
In order to ensure the structural integrity of the pontoon shape was divided up into 4-inch intervals. Each interval was assigned a cross-sectional area, assuming a hollow rectangular cross-section, and its volume was recorded to calculate the distributed buoyancy force. This distributed buoyancy force was combined with the reaction loads to create the shear and moment diagram seen here. It was determined that the stress was far below the yield strength of the fiberglass material, meaning that the number of layers was a function of impact and abrasion resistance only.
The bridge subassembly is composed of custom water-jet middle brackets, aluminum tubes, plywood platforms, and additional hardware. The solar panels are raised to provide storage as well as to minimize the pilot's shadow that strikes the top of the solar panels.
The free body diagram shown here was used to determine the stresses in the two main bars that span the pontoons. The main load in the middle accounts for both the rider and all required safety equipment. The 20-pound load on either side accounts for the solar panels, and the reaction loads were placed 8 feet apart at the maximum width of the pontoons. It was determined that with these loads at these locations, the 6061 aluminum beam used would have a 1.7 factor of safety.
The middle bracket component allows the pontoon subassembly to move relative to the bridge subassembly, and the solar panel mount lets us take the solar panels on and off whether we're doing the endurance or the sprint race.
The manufacturing plan used to create the pontoons was quite similar to how high-end surfboards are created. We shaped foam blanks to the exact size using a hot wire cutter, then sanded and laminated with fiberglass and epoxy resin.
In order to mate the modular components of the boat, a series of brackets were made. All brackets were water jet cut and then bent, some bent with a finger brake and others with a series of mallets and wooden forms. In order to manufacture the bridge, all aluminum components were cut to the proper length. They had holes drilled in at the required locations and then were assembled using brackets. A plywood sheet was added on top to support the driver and all required safety gear. The entire system was extremely modular, and we ourselves put it together and took it apart many times throughout the process.
While we weren't able to perform our testing procedures, we had plans to do a bridge load test, a leak test for the pontoons, and then run tests adjusting the bridge position versus speed and turning radius to optimize performance before the race weekend. Although we weren't able to race our boat, we all found the senior project experience to be extremely valuable. Here are some of our takeaways.
The main lesson that I learned from this project was not to use a hand drill on metal parts. It's always worth the little bit of extra time to slow down and do it properly with a drill press or a mill rather than trying to do it by hand.
One thing I would take away from this project is how big of an impact a good team can have on success. Our team worked very well together and had incredible communication. Team members displayed competence, selflessness, and diligence, making it possible to accomplish everything we did. We even had fun while we were doing it.
My takeaway from this project was how much you can learn in just a 15-minute interview with someone who has experience, and how when you're taking on a new challenge, you need to be a sponge for information.
One of the biggest takeaways from this project was realizing just how many iterations it takes to get a final design that is both manufacturable and falls within the design's requirements.
Thanks for watching.